non-quadratic residues. And we've seen an introduction to them and some initial, improved, few initial facts. So just a quick review of what we've done so far. The definition: if n is a non-zero residue class mod P, so P is an odd prime, so P is a prime number strictly greater than 2. N is an odd residue class. So in other words, n is an element of the multiplicative group modulo P. Then we say n is a quadratic residue. So we've been dealing with this definition for a few weeks, or a few lectures. N is a quadratic residue modulo P means that there exists another element, or there exists an element of the integer mod P such that u squared is equal to n, or u squared is congruent to n modulo. So it means n is a square, or to phrase it another way, n has a square root. N is a quadratic residue. And a quadratic non-residue if there does not exist such a u. Okay. So this is a binary classification of the congruence classes modulo P. In the first lecture, we immediately, just to gain some insight into this, we immediately started looking at some examples of odd primes, the first few, 3, 5, 7, 11, and so on, and looking at which congruence classes were residues, which were. We quickly formulated a conjecture, which we then proved here in 8.1, so in the last lecture, I think, which is half of the elements so the elements of ZP, the multiplicative group mod P, are represented by the congruence classes of the integers 1 up to P minus 1. Half of these are residues, and by implication, half are not. Half are non-residues. And we also proved something which will become theorem 8.3. We haven't worked our way towards stating that, but we looked at the multiplicative structure. Where we showed that if you take two residues and multiply them, you get a residue. If you take a residue and multiply it by a non-residue, you get a non-residue. And finally, you take two non-residues and multiply them. This is what we were proving at the end of the last lecture. You get a residue. When we were discussing this, I persuaded you to think about this very much in the way of how you think about the multiplicative structure of positive and negative numbers. Multiply two positives, you get a positive. Multiply a positive and a negative, you get a negative. Multiply two negatives, you get a positive. And the connection, why that's a meaningful connection, is this is kind of what we're talking about. When you look at positive and negative numbers under normal real arithmetic, another way of looking at it is you're looking at the numbers that have square roots, the positive ones, and the ones that don't have square roots in the real numbers, which are the negative numbers. And so their multiplicative structure is very much mirrored here. It's similar underlying concepts. So that's just a quick recap of what we've done up to now. Is there any questions or clarification I could give on any of these things that we've quickly summarized? hovering around over this is how are we going to answer the typical question of, given a large prime P and a congruence class mod P, how are we going to be able to determine if n is a quadratic residue or not, modulo P? And we have a naive method of figuring out if n is a quadratic residue, and that's just patiently, one by one, search for all the residues by squaring everything modulo P. If you square all of the congruence classes between 1 and P minus 1, square them all, you'll see what all the residues are, and you'll discover whether or not the n is among them or not. But it's a very naive kind of brute force method. What we're looking for is, there any better, more sophisticated way that exploits some understanding of what's going on here that can allow us to answer the question of, is this congruence class a residue or not, modulo P? If the residue, if the n that somebody quotes you, if you recognize it as a square integer, something like 9 or 4 or 16, if you recognize it as a square integer, then yeah, you know straight away it is a quadratic residue because it's the square of its integer square root. But the harder question is, like if I give you a large prime, 101, so let's say, and I ask you, is 5 a quadratic residue modulo 101? Well, there's nothing that immediately leaps off the page that tells us whether or not 5 is a quadratic residue modulo 101. Okay. We can go ahead and square everything modulo 101. Square all the congruence classes up from 1 up to 50. Square them all, and we'll discover what all the quadratic residues are modulo 101, and we can look and see whether 5 is among them or not. But that feels like a kind of unthinking kind of method. Is there anything better we can do? So that's the kind of thing we're working towards in this chapter. Okay, so now what we're going to do is introduce some notation. So this is section 8.4. And this is the Legendre symbol. This is definition 8.2. So this is some useful notation for working with residues. And this is what the notation looks like. It's a pair of parentheses and n straight line p. The straight line is the same symbol we used for divisibility, but it doesn't mean divisibility here. Here it's part of the Legendre symbol. This thing takes, well, we mostly think about it taking the values plus or minus 1. But we extend it so that we say it takes the value 0 if p divides n, i.e. if n is congruent to 0 modulo p. With the other values, we're going to say it takes value plus 1 if n is a quadratic residue mod p. And minus 1 if n is a quadratic non-residue. It's kind of what we call like a kind of indicator function. Kind of indicator function for quadratic residues. In the notes on page 57, you'll see a discussion about the notation that we use for the Legendre symbol there's no universal agreement of it. There's at least 2 different versions. Some books, some authors write it like this. Other authors write it as like this. I've taken the decision in this course, we're going to write it like this. That's the notation they use in Tom Apostle's book, which I'm roughly following for some of our material here. But other books write the Legendre symbol like this. I mean, both can be confused with other things. This thing, you can look at it and it can kind of confuse you and you think of fractions and n over p, fair enough. This one you can look at, you can confuse you with divisibility statements. Okay, we're not saying n divides p here. That's not what we're saying. It's a different use of the straight line symbol. So both of them can be confused with other things. So maybe not too much to choose between. But in this course, I'm just going to decide just to stick with that notation. But if you open other number theory books, you may well see them make use of this notation for the Legendre symbol. Okay. Okay, so for just to see some examples of its use. From our examinations mod 7, from our investigations mod 7, we would see that 1, 7, these Legendre symbols, 1, 7, 2, 7, and 4, 7, these are all +1, because 1, 2, and 4 are the quadratic residues mod 7, and 3, 5, and 6 are -1. 3, 5, and 6 are the quadratic non-residues, much the same. Lemma 8.2, you can immediately say that, well, this kind of thing is always going to be +1. M squared is clearly a quadratic residue because it's the square of n. Provided m is not congruent to 0 mod p. But if m is a non-zero congruence class, then m squared is definitely going to be a quadratic residue. It's a funny thing, this Legendre symbol. I mean, you can think of it at the moment as it's just kind of a shorthand way of writing n as a quadratic residue mod p, because you just write n mod p brackets equals +1, and that says n is a quadratic residue. If you write n mod p brackets equals -1, that says n is a quadratic non-residue. So in some sense, it just looks like a compact form of notation. But it's a sensible kind of notation to use because it is this kind of function, this kind of indicating function, indicating a +1 value for a residue and a -1 value for a non-residue, does have some nice properties. So this is theorem 8.3. Now we've already proved this. This is what I was referring to up here. When we proved the multiplicative nature of the residue, non-residue classification, what we've effectively proven, previous work has proved that actually the Legendre symbol is what we say it's multiplicative. If you think of this thing as being, so you think of p as some fixed number, it's a fixed prime modulus, and then the Legendre symbol becomes a function of the first argument. Yeah, it's a function of the first position that takes values in +1 or -1 or 0. Well, what we've done before in proving that if you multiply two residues, you get a residue. If you multiply a residue and non-residue, you get a non-residue. Multiply two non-residues, you get a residue. That effectively means that you can say this, that the Legendre symbol is multiplicative. Multiplicative in the first position. First position means there's like two positions in the Legendre symbol, the modulus and the congruence class. If you think of it as a function of the thing that goes in here, it's a multiplicative function. If you put a product of numbers n times n there, The Legendre symbol of the product is the product of the Legendre symbols. So that's nice. It's definitely not linear or anything. It's definitely not the case of the Legendre symbol of n plus m is Legendre symbol of n plus Legendre symbol of n. That isn't true at all. It's a multiplicative. You can see how it works with what we've proved before. Because when you multiply two residues, you get a residue. So if n and m are residues, that means these two Legendre symbols are both plus 1. So when you multiply them, you get plus 1. And that agrees with the fact that n times m is a residue. If n and m are both non-residues, if they're that third case there, if they're both non-residues, then both these Legendre symbols are minus 1. So when you multiply them together, you get plus 1, which agrees with the fact that the product n times m is a residue. Yeah, that third case. And the middle case, when one of them is a residue and the other one isn't, one of these symbols on the right-hand side is plus 1, the other one is minus 1, so their product is minus 1. And that agrees with the fact then that the product n times m is a non-residue, which is that middle case that we proved last time. Okay. And there's an alternative, or there's just a differently worded proof given in the notes, but it's more or less comes down to the argument that we presented last time. Okay. So the proof in the notes is slightly different. Really, it uses the same principles, but it's just organized slightly differently. But we proved that last lecture. Okay. So that's our Legendre symbol. Also note, as well as being a multiplicative function, also note that if n is congruent to m modulo p, then the two Legendre symbols have to be equal. Yep. Because our definition of being a quadratic residue is a statement about the congruence class represented by n. So if n and m are coming from the same congruence class mod p, they're clearly going to have the same value. Okay? Because if there's something that gives you, if there's a u that when you squares it gives you n mod p, well, it also gives m mod p, because they're congruent. Okay? So as well as being a multiplicative function, it's also here you see really it's a function on the congruence classes modulo p. So two things are congruent. The two Legendre symbols are going to be the same. So that just follows from the proof of from the definition. Definition of quadratic residue. So our basic question that we're faced here is, how do we evaluate the Legendre symbol? How do we evaluate the Legendre? How do we figure out if a given congruence class n is a quadratic residue modulo p or not? And you can kind of view the rest of the chapter as one way of thinking of the results in the rest of the chapter are various steps or various ways of answering that question. Okay. And the next theorem we're going to look at gives a rather explicit answer to that question. It gives you a kind of a formula for it. So this is Euler's criterion. So this is just some motivation for Euler's criterion, which is the next theorem. So motivating Euler's criterion. So first of all, we want to recall a result we've already looked at and one that you've been using in the cryptography part, which is Fermat's little theorem. Okay. Fermat's little theorem. So Fermat's little theorem says that as long as P does not divide A, then A to the power of P minus 1 is congruent to 1 modulo P. Okay. The more general form of that is what we referred to as Euler's theorem, which was A to the power of phi of n, phi of the modulus, if n was the modulus, so more general modulus, not necessarily a prime number, and A to the power of phi of n was 1, where phi was the Euler-Tauschen function. In the special case of a prime modulus, it reduces to this statement, A to the power of P minus 1 is congruent to 1 mod P. Well, this has an interesting congruent consequence. If you take the square, well, if you kind of take the square root of both sides. So instead of A to the power of P minus 1, you consider A to the power of P minus 1 over 2. Now remember, P is an odd prime. P is a large prime. It's strictly bigger than 2. So P minus 1 is even. So when you divide it by 2, you get an integer. Well, what are the possibilities for this thing modulo P? Well, you can think of it as you're effectively taking the square root of both sides. You know, if you take this thing and square it, you get back to A to the power of P minus 1. Yeah, if you square both sides, raise this to the power 2, well, the 2 multiplies this, so it cancels the 2, and you're back to A to the power of P minus 1. So when you square this, you get 1. So that means this must be plus or minus 1 modulo P. Okay? Because it means that this is the solution to x squared congruent to 1. And we know that the polynomial x squared congruent to 1 mod P, because it's a prime modulus, that quadratic polynomial has at most 2 solutions. It definitely has the solutions 1 and minus 1. So they are the only solutions. So A to the power of P minus 1 over 2 must be plus 1 or minus 1 modulo P. Now this is very interesting because we've just gone to the trouble of defining the Legendre, which is our indicator function, which gives you values of plus 1 or minus 1, depending on whether n is a quadratic residue. Oh, yeah. And here we've got another device or quantity, yeah? Another device or quantity that gives you plus 1 or minus 1. Moreover, if A happens to be a quadratic residue, i.e., if A is congruent to, let's say it's the square root of B. Remember, a quadratic residue, if A is a quadratic residue, it means it's the square of something. So if A is already a quadratic residue, then when you do A to the power of B minus 1 over 2, what you're doing is B squared to the power of P minus 1 over 2. And what's an interesting way to write this? Or a simpler way to write this on the right-hand side. B to the power of P minus 1, yeah. So when you multiply the exponents, the 2's cancel. B to the power of P minus 1. And this must be this must be 1 by Fermat's little theorem. Anything raised to the power of p minus 1 is going to be congruent to 1 modulo p. So that last step is by Fermat's little theorem. So this looks even better. Here's this formula that outputs plus or minus 1. If A is a quadratic residue, it gives you plus 1. So then you got to think, well, so what if A was not a quadratic residue? So if it's a non-residue. A to the power of p minus 1 over 2 is congruent to what? Mod p. Well, it must be plus or minus 1. We've already decided. So could it be plus 1? This is the tough question. Could this still be plus 1 if A was not a quadratic residue? Or would it have to be minus 1? Well, this is where we can do a counting argument. How many quadratic residues are there? P minus 1 over 2, yeah, half. Half of the congruence classes mod P are residues. So here when I said, well, suppose A was a residue, then A to the power of P minus 1 over 2 is congruent to plus 1. So if A is a residue, it's a solution of x to the power of minus 1 over 2 congruent to plus 1. Now that polynomial, this polynomial you're looking at from the very left to the right there, has degree p minus 1 over 2. And Lagrange's theorem tells us that a polynomial modulo a prime, the number of solutions it has is bounded above by the degree of the polynomial. So here we're looking at a polynomial like x to the power of p minus 1 over 2 congruent to plus 1. It does have solutions. Anytime you give it a quadratic residue, A, it's a solution. And there are exactly p minus 1 over 2 such A's. There are p minus 1 over 2 distinct congruence classes modulo P that are quadratic residues. Each of them is a solution to this polynomial, x to the power of p minus 1 over 2 congruent to plus 1. So they must be all of the solutions. There's no more room for other solutions. So our non-residue cannot give us the value plus 1, because that would be too many solutions to this polynomial, which is degree p minus 1 over 2. So a to the power of p minus 1 over 2 cannot be plus 1, so therefore it has to be minus 1. If A is a non-residue. It has to be minus 1 mod P. So this is in the case where A is not a residue. As the P minus 1 over 2 residues are all the solutions to x to the power of P minus 1 over 2 congruent to plus 1 mod P. And that's by, what's it called, Lagrange's theorem. So we have this counting argument again. If A is a non-residue, it has to be minus 1 because the available slots for solutions of something to the power of p minus 1 over 2 giving you plus 1, they've already been filled by the p minus 1 over 2 quadratic residues. So if it's a non-residue, it's not one of those, so it has to be the other value, minus 1. So to recap there, what we've done is we've taken Fermat's little theorem, taken the square root of both sides effectively, we're looking at this thing, that anything to the power of p minus 1 over 2, it either gives you plus 1 or minus 1 modulo p, or at least when a is a non-zero congruence class, modulo p. And it gives us plus 1 exactly when a is a residue, and minus 1 exactly when a is a non-residue. So this establishes theorem 8.4, which is known as Euler's criterion. Euler's criterion is that n, the Legendre symbol n mod p, is congruent to n to the power of p minus 1 over 2 mod p. And the proof is basically this argument we just given here. Looking at the polynomial, x to the power of p minus 1 over 2, congruent to plus 1, congruent to minus 1, and making use of Lagrange's theorem. And the fact that there are p minus 1 over 2 residues, p minus 1 over 2 non-residues. So the proof here is more or less what we have above. The details are spelled out in full in the notes, but it's just more or less what we were discussing there. So this is a much better situation to be in, right? Previously, we were faced with the question is, what is the value of n mod p of this Legendre symbol? We didn't have any sophisticated techniques. We could maybe just dive in and calculate all the quadratic residues and just inspect and see if n was amongst them or not. And that would tell you whether this was plus 1 or minus 1. But now we've got a kind of a quantity. It's a power of n. A meaningful power, half of the value p minus 1. So you can evaluate, you can work out this congruence class and figure out is it plus 1 or minus 1 mod 1. Now this, for p large, this still might be a computationally tough task maybe. If p is very large, you've got to do a lot of multiplications to evaluate this congruent, to evaluate this integer, or evaluate this congruence class. If p happens to be very, very large. But at least it does give us a lot of insight into when things are residues and when things aren't. Okay, so the residues n are exactly the congruence classes for which this value is plus 1 mod p. And the non-residues are exactly those congruence classes for which this is minus 1 mod p. If you put in any n in here, which is non-zero mod p, this quantity will always be plus 1 or minus 1. So from Euler's criterion, it's a good insight, and it gives you access, and it gives you a way to attack these Legendre symbols and work with them. So straight away, we can see our first application of it. So in theorem 8.5, we settle the question of when is minus 1 a residue mod p. So in other words, we're looking at p minus 1. Minus 1 mod p, that's the congruence class of p minus 1. When we looked at our examples, when we looked at p equals 3, 5, 7, we looked at 11 as well in the lectures. In a couple of them, we maybe found that minus 1 was a residue. In the other one or two of the others, it wasn't. So we've already seen that sometimes it is and sometimes it isn't. Here, 8.5 gives you a very nice condition for understanding when this is plus 1 and when it's minus 1. And it just goes on the congruence class of the prime modulo 4. Okay. Now, even if p is very large, you can tell immediately, I mean, if you can see the digits of p, you can tell immediately what it is modulo 4. Remember, 100 is a multiple of 4. So to work out something modulo 4, you only have to look at its least significant 2 digits, so its tens and unit digits. because the hundreds, thousands, etc., they're all congruent to 0 mod 4. So you just look at the last two digits here, work out what those are mod 4. So this is a very easy test to do on a given prime number, work out whether it's 1 or 3 modulo 4. Obviously, any odd prime number has to be one of these two. So it can't be 0 mod 4, it can't be 2 mod 4, because in those cases it would be even. P is an odd prime number. Now the proof of this is just a direct application of Euler's criterion. From Euler's criterion, we have -1, the Legendre symbol -1 mod P is congruent to -1 to the power of P minus 1 over 2 mod P. Now Euler's criterion says that these are congruent. But in this case, when you're dealing with -1, you can actually say a little bit more. You can actually say they're equal. Because the thing on the left is by definition +1 or -1, depending on whether -1 is a residue or not. But the thing on the right is a power of -1. Well, powers of -1 are either +1 or -1. You can't get anything else from the power of -1. So in fact, these must be equal. Because the thing on the right-hand side, is either +1 or -1. And when is it? Well, powers of -1 and +1. I mean, you know when they come out +1 or -1. When does the power come out +1? When the exponent is equal. So that's in the case of P minus 1 over 2 is even. And it comes out as -1 when P minus 1 over 2 is odd. Yeah. Well, i.e., you can rewrite those conditions as saying P minus 1 over 2 is 2 times n for some n. Or P minus 1 over 2 is odd. So if it's odd, it's 2 times n plus 1. Some n. But you can rewrite those conditions. Well, just reorganize. So here you get P is 4n plus 1. Multiply across by 2. Here you get P is 4n plus 3. So that gives it to me. P is congruent to 1 mod 4, you get +1. P is congruent to 3 mod 4, you get -1. Yeah, so this is just a simple observation that even powers of -1 are +1, odd powers are -1. So P minus 1 over 2 even, P minus 1 over 2 odd, but then you look at that, and then you clear the denominator, and now you're looking at the congruence class of P mod 4. So that's just the first application of Euler's criterion, right? We've kind of got total understanding of when -1 is a congruence class, when -1 is a residue one. It just comes down to the status of the prime P modulo 4. So next time, I think we'll begin. When I see you next week, we'll have a couple of lectures on this. So the thing we'll start with is answering the question of 2 mod. Being able to say when 2 is a quadratic residue modulo. Now, I've still just got a couple of minutes, but I just want to show you one thing, which is just going to look ahead to the culmination of the chapter. In general, we're going to be faced with the problem of working out whether n is a quadratic residue modulo P or not. But we already know that the Legendre symbol is multiplicative. We proved that. And we already have in our course a very clear way of understanding an integer multiplicatively. That is through its prime factorization. So this is the prime factorization of n. Okay. Every integer has a prime factorization. Well, we've just proved that the Legendre symbol is multiplicative. But if you see a product of elements here, you can split apart the Legendre symbol as the first Legendre symbol multiplied by the second. Well, that generalizes to a product of any number of factors. So here you've just got a big product operation, and all these exponents are just big product operations. So that's from the multiplicative property. So from that small little thing we did about multiplying residue by residue, residue by non-residue, multiplying non-residue by non-residue, that is immensely powerful and simplifying here. You can kind of see now that the question of what's the value of this Legendre symbol n mod p all hangs on, turns on, what is the value of the Legendre symbol of one prime modulo another one. Indeed, you can go a little bit further. These alpha i's, these are powers, and remember this Legendre symbol is either +1 or -1. So if those alpha i's are even, then this will automatically be +1. So you can drop it from the product. So really, you only need to consider the product where over the I such that the alpha I is odd. And in that case, you don't need the odd power anymore because, well, if this is +1 to an odd power is +1. If this was -1 to the odd power is still -1. So all the even powers that are here, you can just forget about them because they just contribute +1s. It's only when the power is odd you have to worry about it. And in that case, it just comes down to what's the value of this prime, what's the value of the Legendre symbol of this prime modulo another. Okay. So everything hangs on these values. And what we're building up to at the end of the chapter is something that will unlock this and give us a method for, or give us a way to exploit these first few steps, and within a short few more steps get an actual answer out, +1 or -1 to this general question. But this is quadratic reciprocity, and it's a kind of a spooky connection. You can look ahead and see what it actually is, what quadratic reciprocity, what it actually says. But it gives you a spooky connection between the value of the Legendre symbol of one prime modulo another one and its reciprocal, the Legendre symbol of Q modulo P. So this one refers to the residue status of P modulo Q. This one refers to the residue status of Q modulo P. And I say spooky connection because from the definition of quadratic residue, there's nothing in it that screams out that there should be a connection between these two things. So it's a little bit mysterious, and it's quite a deep principle in mathematics, and it has lots of consequences, and it opens up a lot of number theory and algebraic considerations, that there is a strong explicit connection between these two things of whether P is a residue modulo Q and whether Q is a residue modulo P. So that's something we're going to be working towards, and that will unlock these few steps here, together with the principle of quadratic reciprocity, will allow us to continue this sequence of equations and more or less get a kind of a quick algorithm for working out the value of this Legendre. So that's kind of what we'll be advancing towards over the next few lectures. Okay, I'll leave it there for this afternoon. I'll see you all later in the tutorials at 4 and 5. Oh,